cities and industries start electrifying, it is only natural that the demand for energy storage rises. The projected demand for the energy storage can be seen through the global battery market statistics, which is projected to grow to over twice its current size, that is to over $300 billion by 2033. Secondary batteries are dominating that with 78.2% market share due to their rechargeability. So how do we meet that demand? We meet that demand from other sectors. Humanity produces around 56 million metric tons of sunflower shells annually, and 20% of that goes to waste, into sunflower shell wastes, which are often discarded in landfills and left to accumulate, or even worse, burnt into the open atmosphere, releasing gigantic amount of carbon dioxide and other pollutants into the atmosphere. So how can we utilize that into making batteries, and what can we do about that? Well, before we get into that, let's talk about what we currently use for batteries, lithium-ion batteries. They're the most successful battery technology, and their performance is undeniable. However, they do have their bottlenecks. Mostly, lithium reserves are limited, so lithium is expensive and the supply chain is volatile. Additionally, lithium can be a fire hazard risk in some cases. So what do we do when lithium is not enough to meet our needs? Let's look at all the battery structures that are available to understand how we can address that and what angle we can come from. There are batteries that work with potential energy, thermomechanical energy, kinetic, chemical, thermal, but we will be focusing on electrochemical batteries, specifically zinc-ion batteries. We have discussed the limitations of zinc-ion batteries, of the lithium-ion batteries, but zinc-ion batteries have potential. They're safe, they're eco-friendly, and they're low cost. They have a high theoretical capacity, and they're perfect for grid-scale energy storage, as opposed to lithium. However, for that, there needs to be research on the cathode design. Vanadium-based cathodes have gained a lot of interest in research. They have high capacity and multi-electron redox activity, which is promising for the next generation of aqueous zinc-ion batteries. And however, there are major challenges with zinc-ion batteries that we cannot deny. They have low electric conductivity, and they have the potential for structural degradation. So we will be focusing on the research gap and what we need to optimize through surface modification, interlayer engineering, and composites. Let's compare zinc to lithium to see how zinc is advantageous in this situation. If you look at the cost column, you see that zinc is $2.65 per kilogram as opposed to lithium's $163 per kilogram. So zinc is much cheaper. However, it has the same radius, roughly the same radius, which means it can be useful in similar applications. Now my colleagues will further highlight the scientific gap and the correlation.
Thanks, Viras. So, now we come to the mechanism or the chemistry of the aqueous zinc ion battery. It actually consists of two mainly parts, the cathode part and the anode part. The cathode part is where the reduction for the zinc occurs. It's like in the first equation, the zinc is with our material R V₃O₇, where R here represents GO₃W, which is graphene oxide tungsten. And in the anode part, the zinc is oxidized. So then we will have at the end the overall reaction as illustrated in equation number 3. So now when we want to discuss about the cathode, cathode firstly usually consists of the three main things: the active material, which stores the charge, the binder, where it connects everything in the battery, the conductive additive. And conductive additive is the one that is moving the electrons. And the common material is carbon black. Carbon black actually is a petroleum based, which is environmental harmfully and has impacts. Also, it's expensive. So we come up with an alternative material, which is the sunflower shells. Sunflower shells is rich of carbon, so it's a good raw material as a replacement of the carbon black, and it will be converting to carbon material, activated carbon, through a thermal process.
Thank you, Muhammad. To test our idea, we designed the cathode with specific material characteristics. Our core cathode architecture is composed from graphene oxide sheets in addition to tungstate intercalated in vanadium oxide in addition to sunflower shell carbon. The mass ratio of our electrode composition is 70% from the active material, 20% from the sunflower shell, 10% from the PVDF binder. On the right side of the slide, we have an explanation of how the entire battery was assembled. Let's move to the material characterizations and electrochemical measurements, starting with the SEM micrograph, where we have 4 different magnifications between 100 micrometer until 1 micrometer. Then we have the XRD and FTIR. On the left we have the XRD plot, where we have the most intense peak at around 21 to 22 degrees, indicating successful binding of graphene oxide and tungstate in the V₃O₇. Additionally, we have several sharp peaks indicating the crystallinity of the material. On the right side we have the FTIR plot, which shows the functional groups in the material. We have a peak at about 750 wave number, indicating the presence of the graphene oxide. On the left side of the plot we have smoothness, showing that the material is dehydrated. Next is galvanostatic charging and discharging and energy discharge plots. On the left we have the GCD, where we activated the battery for about 2 cycles. Then we tested for the specific capacity, which returned 248 mAh per gram. After about 100 cycles, the specific capacity dropped to around 225 mAh per gram. The testing is still going, as you are going to see soon in the video. Throughout the cycles, we maintained an efficiency of 100%. On the right, we have the energy discharge, where we started with about 1.2, and after 100 cycles, it dropped to about 0.85. Then we have the electrochemical impedance spectroscopy and cyclic voltammetry. For electrochemical impedance spectroscopy, we can extract 3 important information. The first is the solution resistance, which gives us about 18.9 ohms. Second is the charge transfer resistance, which gives about 169 ohms. And lastly is the Warburg impedance, which gives about 475 ohms. Cyclic voltammetry shows the redox nature in the battery, where we have the upper peaks for the oxidation in the anode, when we have the lower peaks for the reduction in the cathode. It also shows the potential and current for those peaks. The highest anodic peaks shows the current of around 3.5, which is higher than the highest cathodic peak, whereas the second anodic peak shows a current of around 1.3 milliampere, which is lower than the second cathodic peak. Finally, we have the percentage contribution, where the battery can be either diffusion controlled or capacitive controlled. At a scan rate of 0.1 millivolt per second, the battery showed a diffusion controlled behavior of about 55%. When we increased the scan rate to 0.4 millivolt per second, it showed a capacitive controlled behavior of about 61.8%. When we increased the scan rate to 1 and 2 millivolt per second, the capacitive percentage kept increasing. Let's move now to a video recorded in the workstation where the electrochemical tests were performed.
So we are fabricating a button cell battery. The first step is to cut each component in the appropriate size. We move then to the crimper, where we bind all components together. It will look something like this. This is the GCD machine, where we charge and discharge the battery for a number of cycles. If we show the data, we can view the performance of each cycle, where we show current and voltage. We can show the most recent cycle as well for current versus voltage. To show the entire process, we're going to have something that looks like this. We can as well show the specific capacity versus efficiency for each cycle.
What makes our project especially powerful is that it sits at the intersection of 3 main priorities that define the next generation engineering solutions: sustainability, performance, and cost. First, sustainability. This work gives a new value to an abundant agricultural waste stream and reduces the dependence on fossil-based conductive additives and contribute to a sustainable and safer environment. Second, performance. By using a functional carbon additives derived from biomass, we are targeting a real electrochemical role inside the battery cathodes, not just as a symbolic green ingredient, but as an engineered component. Third, cost. Low-value waste biomass offer a promising solution toward affordable battery material, especially for large-scale battery storage technologies where cost competitive is essential. Together, these three main pillars make our project broadly relevant, because strong research does more than solve a narrow technical problem. It connects material science, electrochemistry, environmental responsibility, and practical impact. And that is exactly what our project does. At the end, this project tells a simple but powerful story. A waste material, usually overlooked or discarded, can be reimagined as part of the future energy storage technology. From sunflower shells to conductive carbon to zinc-ion battery cathodes to cleaner and safer energy storage. This is more than a battery material study. It is a vision for how waste can become a value, and how sustainability can drive innovation, and how engineering can help build a cleaner future. Thank you all for your attention and consideration.